Section 22.4 talks about the Claisen condensation, however you think about this. Now, let's review a little bit about what's going to be happening here, okay? Remember that we can transform ketones into enolates, which are therefore nucleophilic, okay? Aldehydes also can be transformed into enolates with an appropriate base, LDA, sodium ethoxide, sodium hydroxide, something like that. Enolates make great nucleophiles. They're negatively charged on the carbon, and the carbon atom acts as the nucleophile. What we are going to see that's new is that esters can be converted into the enolates. Okay, so here's an ester. It has alpha hydrogens, okay? And we can convert this with sodium ethoxide into an enolate. And enolates, yes, you have guessed it, are great nucleophiles, okay? So we're gonna do this reaction next. The second thing I want to jog your memory with is that esters react by nucleophilic substitution. So for example, if we have a nucleophile and we want to attack an ester, we know that the nucleophile is going to attack this carbon atom, which is delta plus, right? Oxygen is delta minus. And so you get a tetrahedral intermediate. Where your nucleophile has attached to that carbon, okay? And then you have fragmentation to kick off the leaving group, okay? Methoxide, for example. And that's gonna give you a substituted product, okay? So this was the subject of a whole chapter. This is called Nucleophilic Acl Substitution because you're using a nucleophile to substitute something on the acyl group of a carboxylic acid derivative, okay? So we're gonna combine this concept here with this concept here in a reaction called the Claisen condensation, okay? So the Claisen condensation is a reaction where you take an ester and you treat this with sodium ethoxide, H3O plus, and you get this guy here, okay? Now the equation is not balanced. I suppose I could do that. You're going to have ethanol as a byproduct here, basically, okay? And if we wanted to kind of balance it, we'd put a 2 there, okay? So let me take you through the curved arrow reaction mechanism here. It's very critical that you're able to draw this and understand this. And it's basically review. It's review of everything we've talked about so far, okay? So step 1, you have your starting ester, okay? And you need to recognize that this is the alpha carbon and we have alpha hydrogens available here, okay? And we have a strong base, sodium ethoxide. So sodium ethoxide is an alkoxide. The sodium atom is of course a spectator ion, so you just leave it off. The negatively charged oxygen is a suitable base to deprotonate this, and you form the enolate. So I call this step deprotonation. And technically this is in, equilibrium here, okay? So what we get is the enolate of our ester, okay? And that's a nucleophile. Now, what we need to do is line this up next to another ester molecule. And and we want to perform nucleophilic acl substitution on this ester, okay? So this whole molecule is a nucleophile, and we want to substitute that group for that whole nucleophile, okay? So let me show you how that works. Take the negative charge, attack the carbonyl carbon, okay, to give you the tetrahedral intermediate. The tetrahedral intermediate will collapse by expulsion of the ethoxide. So E is elimination, okay? All of these steps technically are still in equilibrium, okay? And so what you get here is ethyl acetoacetate. Okay, maybe I should name these. This is called ethyl acetate as an example of an ester, and this molecule is called ethyl acetoacetate. Okay? Now we have this ester, this keto ester, so if we label it, this is a beta keto ester, okay? I forgot the oxygen. Okay, so beta keto esters are acidic, okay, because there's that alpha hydrogen in the middle of the molecule that can be deprotonated quite readily, okay? And this is the step that's not in equilibrium. Well, it strongly favors the products here. So this is the driving force for the whole reaction. Once sodium hydroxide comes in and sees this much more acidic hydrogen, it deprotonates, okay, to give you this guy here, okay? And this just is resonance stabilized. It's hanging out in the reaction and it just stays there, okay? So every time ethyl acetoacetate forms, sodium hydroxide deprotonates it, and you get this molecule in the box, okay? And it funnels off onto that direction, okay? So that's all step one, okay? So that's D-A-E-D. And that happens all in step one when you add sodium ethoxide in ethanol solvent with ethyl acetate. You add H3O plus to protonate this and give you the final neutral product. So if you need another letter for that, we can call that P for protonation, and we'll put that at the end, okay? So you protonate and you basically work up the reaction mixture to return it to a neutral pH, okay? So that's the Claisen condensation. It's a carbon-carbon bond forming reaction. You're forming this new bond, and it's a synthesis method for making beta keto esters, okay? Beta keto esters. Now, as you can imagine, you can take any ester you want, okay? You can take something with maybe, 3 or 4 carbons, okay? And treat this with sodium methoxide, okay? And you need to plan ahead what you're going to be doing, okay? So here's the alpha carbon, and remember that that's going to be the nucleophile. So how do you figure out what's being formed? Well, that's the nucleophile, and then you need to sketch out another molecule below this, okay, with the same, shape and number of carbons, okay, and this is going to be the electrophile, okay. So this carbon is going to connect to that carbon, and you're going to kick off the methoxy group, okay. So the product you're going to form here, if I can use dots again to help orientate our eyeballs, this carbon is going to be connected to that carbon of our ester, which changes to a ketone when you kick off methoxide, okay? So you're going to form that molecule right there, okay? okay? So get in the practice of drawing these out, maybe making dots, maybe counting carbons, labeling alpha or beta, or drawing curved arrow reaction mechanisms. There's 4 or 5 different ways to figure out how these things get connected. It does require practice. I don't expect people to see me show this on a video once and then they're just like experts for the rest of their life. It takes review, it takes practice, and it takes some thinking, okay? Now let's talk about the crossed Aldol reaction. I'm sorry, cross Claisen condensation. I was thinking that this is similar to the crossed Aldol reaction. You can get lots of different products if you mix 2 different esters, okay? So if you have an ester that looks like this, and you have an ester that looks like this is gonna give you 4 products. It's gonna give you a terrible mess, you know, 25% yield of one, 25% yield of the other, and you're gonna have to do distillation to separate them all, and it's just a hassle, it's useless. So what we wanna do is control this, okay? You control the reaction by using one component that has no alpha hydrogens. So there are various possibilities for this, okay? One might look like this, okay? You can see how this ester has no alpha hydrogens. You could also react it with something like this. This technically isn't an ester, but you could react it with something like that. Or you could have something like this, okay? That has no alpha hydrogens either because the carbon on the left, which is the alpha carbon, is bonded to a whole bunch of methyl groups. But that might have reduced reactivity because the tert butyl group is rather sterically hindered. Okay, so let's see how that works. If we take ethyl acetate and we treat this with ethyl benzoate, in sodium ethoxide, we are going to form a molecule that looks like that, okay? So how does this work? Let's review. Let's just go through the mechanism again. If you've got this, fast forward or just go play a video game or something. But here, this is the alpha carbon, and we have ethoxide, which is the base. So that deprotonates here, okay? And that makes the enolate. And remember, because it has a negative charge, it's the nucleophile. This guy here has no alpha hydrogens, so it has no choice but to be the electrophile. Okay, that's very important. So this nucleophile attacks the electrophile. So let's position this molecule nearby a little bit. Let's put it over here. All right, so in yellow, I'll show the curved arrows for this. The electrons on this carbon are going to attack that carbon right there, and you're gonna get a bond formation between that nucleophilic enolate carbon and the carbonyl carbon of the ester, okay? So you're gonna get that tetrahedral intermediate. Okay, the tetrahedral intermediate collapses by elimination of ethoxide. base comes in and then that stops and then you add H3O plus, right? So there's a couple more steps here. Remember, you always add sodium methoxide or something like that, and then step 2 would be to add minor amounts of aqueous acid to neutralize the reaction solution, okay? So that's one way to control the reaction. You use a reactant with no alpha hydrogens. Ethyl benzoate is a great example of that, okay? The second way to control the reaction is to use LDA. We call this a directed Claisen reaction. So if I have something like this, and I treat this with LDA, okay, this will make the enolate right here, okay, and I've set that up. That has to be the nucleophile, okay. Then in step 2, if I add a different ester, say this one here with 5 carbons, right? I'm gonna get a product that looks like this. Maybe I'll color code it here so you can see what's happening. Okay, so that nucleophile attacks the green molecule here, which is the electrophile. Okay, and you're going to get that product. Okay, so that's a great way to control the reaction. You use LDA, selectively react that with one of your aldehydes. It's going to make the enolate, or selectively react it with your ketone. That'll make the enolate, or selectively react it with an ester. That'll make the enolate. Okay, so there's just a lot of parallel kind of analogies, and it's kind of repetition at this point. Okay, we just call it the Claisen. Okay. Now, let's talk about the intramolecular Claisen reaction. This is named after somebody. It's called the Dieckmann cyclization. Okay, so these were named after famous organic chemists that figured things out and did a lot of reactions and studied this, okay? Now, you still form a beta keto ester, but it's going to be cyclic. So let's take a look at that. So here you're going to be reacting a 1,6 diester, okay? So watch out for these. If you have a 1,6 diester and you react this with sodium methoxide followed by H3O plus, you'll get a beta keto ester. Okay, so here's the alpha carbon, here's the beta carbon, beta keto ester, okay? So how does this work? Let's draw an alpha hydrogen here at carbon 5. We have ethoxide present that is negatively charged. It's a strong base, and it can deprotonate here to give you the enolate. Okay, so let me just highlight some things here. This dotted carbon is the nucleophile because it's negatively charged. We know enolates are carbon-centered nucleophiles. And this carbon here, we know is the electrophile because ketones and aldehydes and esters and all of that get attacked by certain things, attacked by nucleophiles. So that's going to attack itself. Now it looks very far away when I draw it all in a line like this, so it might be helpful to redraw the molecule a little bit so that we see how it kind of curls around. Okay, and so we have this nucleophilic enolate that's going to be attacking this electrophilic aldehyde. And now you can see when I kind of wrap around in a ring, they look closer to each other, and it's going to make a nice stable 5-membered ring. Okay, 5-membered rings, 6-membered rings are nice ring sizes that avoid ring strain. So this negative charge can attack here, okay? And you know, the whole rest of the mechanism is the same as what I've discussed before, okay? Now, so that's the Dieckmann condensation there, okay? So let's see, let's do some practice problems now. So in these problems, we're supposed to fill in the missing question marks, and we want to identify the base that you would use for each of the following, okay? Now what you want to do is you want to match the base with, you know, should we use LDA, should we use sodium methoxide, or sodium hydroxide, or something like that. Now here's an ester, it's an ethyl ester, so we want to use sodium ethoxide, okay? We want to use sodium ethoxide. The book explains why you want to use sodium ethoxide. One of the byproducts might be that ethoxide attacks here, okay? And then kicks off the other group. If you're kicking off ethoxide, which is the same as ethoxide, you're going to maintain the same molecule. Okay? Which is what you want, because you want ethoxide to be in the product. However, what if we use sodium hydroxide? Sodium hydroxide would convert this ethyl ester. Sodium hydroxide is a base, yes, but that would create it would do hydrolysis of the ester to give you the carboxylic acid, which would deprotonate under basic conditions to give you the carboxylate. So we would not want to use sodium hydroxide, okay? We want to use the base that is the same as the alcohol portion of your ester. So here we would want to use sodium tert-butoxide, okay? Let's do problem 29. Problem 29. Predict the product. We want to do a Claisen condensation. So remember, you need two molecules, two identical molecules. So we draw out molecule 1, draw out molecule 2, identify one of them. I'm going to pick the one on the bottom, and I'm going to make the enolate. Okay, that's going to be the nucleophile, and now the one on top is the electrophile. We're going to attack this carbon and kick this off. Okay, so we want to connect those two dotted carbons and just remove the OET. That's all we need to draw. So that's going to look like this. And it doesn't matter how you really draw this, up or down or left or right or something like that. So I'll just go ahead and draw what I have. So here's my nucleophile, okay? And I'm going to connect that to the carbonyl carbon, okay? And I'm going to need a ketone there, and I'm going to need a CH2 and then a phenyl group, okay? So that would be the molecule for A. In B, we do the same kind of thing. Draw two molecules side by side. So we've got this tert-butyl group. We've got this methyl ester. We'll go ahead and draw this, you know, twice. And I'm going to put the nucleophile on the bottom, okay? And the electrophile is up on top. So I'm going to connect these two dotted carbons and remove that. That's all we need to draw. So what do I get? I'm going to get, okay, so there's the bottom molecule with the dotted carbon, alpha carbon. and that's going to be connected to a ketone, and then there's going to be a CH2 and then a tert-butyl group. In molecule C, we do a similar kind of thing. So I'm going to draw this molecule twice. The molecule on the bottom, I'm going to highlight where that alpha carbon is, and the molecule on the top, I'm going to highlight the carbonyl carbon. And so remember again, this is going to be the nucleophile, and I want to kick off this leaving group. So I'm going to connect those two carbons, and I'm going to remove the OET from my drawing. So that's going to give me so here's the bottom molecule, and then I'm going to connect the dots. Okay, there's going to be a ketone, okay, and that's going to be a CH2, and then a carbon, and then the ethyl group, and then an ethyl group off that same carbon. Okay, so count, make sure the branching and everything is the same. So that's the answer for C. Okay, let's do problem 30. Problem 30. We just need to identify the reagents that you would use to produce each of the following molecules, okay? And so what you want to do is identify the ester part, okay? So this whole molecule here is going to be an ester, okay? And this carbon-carbon bond is between the alpha carbon of the ester and the carbonyl carbon of the ketone. So you're basically going to take this bond and break it apart. And remember, the carbon has to have 4 bonds to it. So when you break that off, you're going to form a molecule that is an ester. So just put OET there. Okay, choose the same thing as that one. And the other component is going to be an ester, like this. Okay? Now, these two molecules are both esters, but you should recognize that the molecule on the left is called ethyl benzoate and does not have any alpha hydrogens. So we can just treat this with sodium methoxide, followed by some acid workup to give me that molecule in part A. Okay? So let's go through the same process again, and I'll explain it again how to identify things. So first, you want to identify the ester. Okay, that is the alpha carbon of the ester. This is the carbonyl carbon of the ketone, and you want to break that bond. When you break that bond, make sure that you include an ester. So create an ester. Once again, we want to choose the ethyl ester, which is the same as that fragment. Okay. Now these two components are both going to have alpha hydrogens. Okay. And because of that, we want to use LDA to direct the Claisen condensation. We want this to be the nucleophile because we're kicking off the ethoxy group of the ester on the left. So to do this reaction, we would take this this ester, okay? We would treat it with LDA, then we would add the ester on the left, and we would add H3O+, and that would give us the target molecule shown here on the right, okay? Now, if you got those switched in your mind or you're not sure, it's best to draw the curved arrow reaction mechanism so you can definitely see what's the nucleophile, what's the electrophile, and what's the leaving group. Okay, I've boxed the leaving group. This guy's leaving, okay, when that carbon-carbon bond is formed. Part C, D, and E continue this question. In part C, it looks a little weird, so you might have to draw it out to see that you actually indeed have an ester. Okay, it happens to be the methyl ester, okay? And so again, we follow the same sort of procedure. We identify the alpha carbon of our ester, and we identify the carbonyl carbon of our ketone, okay? We break that bond, and we change our ketone into an ester. Always choose the same methyl ester if you're starting with a methyl ester. And the other component is going to be the methyl ester of this molecule. Okay, with the right number of carbons. Okay, so we have two different esters that both have alpha hydrogens available. So we want to do a directed Aldol reaction using LDA, a directed Claisen reaction using LDA, and the ketone, the ester on the right. Okay, so we take our ester on the right, treat this with LDA, add in the second ester component, add in H3O plus, okay, and that's going to give me this target molecule. Okay, once again, this is the leaving group. Work through the mechanism and you'll see how when you have the negative charge here, this is going to attack and eventually kick that off, okay? So that's how you get this group that's missing, OME group, all right? And I don't quite have too much space on this board, so I'll just do part D, I guess. So let's draw this structure out a little bit better. Okay. Here's the alpha carbon. So we want to break that, and that's going to give us ethyl benzoate. Methyl benzoate. Remember, I want to choose the methyl ester if I have a methyl ester in the product. And the other ester is also going to be a methyl ester with a slightly different R group. And great, the molecule on the left has no alpha hydrogens, so I can just treat this with sodium methoxide. Remember, you want to choose the same OME, right? And then H3O plus, and that's going to give me the target molecule shown there in part D. Okay? Let's do problem 31, which is the D problem 31. All right, so let's count some carbons here, okay? So remember that, well, since this molecule is symmetrical, the top and the bottom are going to be the same, right? Because they're both attached to that aromatic ring in a symmetrical way. So I'm going to call that the alpha carbon, which is going to be the nucleophile. That's carbon 1, 2, 3, 4, 5, 6, and that's going to attack this carbonyl carbon, go through the tetrahedral intermediate, and eventually kick off ethoxide, right? So we're going to form a bond here, and we remove the OET. So what do we get? 7-member rings become fun to draw once you're able to do that. So something like that, I don't know. And so here's my alpha carbon here, okay? And that's going to be carbon 1, I labeled it, and that's going to be OET, all right? And then 1, 2, 3, 4, 5, 6, 7 is going to be right here, okay? And that's going to be my ketone. So that's a 7-membered ring. Pretty cool, huh? All right, in molecule B, we want to also count carbons. So here's my alpha carbon, and let's label and count. Okay, so that's going to be 5 carbons. So I want to connect the alpha carbon to this carbonyl carbon and remove that from my drawing. So that's a 5-membered ring attached to a 6-membered ring. So let's draw the phenyl ring. let's draw the 5-membered ring. And let's count. So here's carbon 2 and 3, according to my drawing. Carbon 4 is here, carbon 5 is here. Remember, that's where my ketone is. I don't draw the OET there. Attached to carbon 1 right there is going to be a line or a bond to my ethyl ester. Okay? One way to check these problems is to make sure you have a beta keto ester. Okay? So here's the alpha carbon next to the ketone, and the beta carbon should be part of an ester. So this is called a beta keto ester. Okay? Or the other way actually, but yeah. The beta carbon is a keto group. In part C, it looks really long and everything, but just count and identify which carbons might be attacking what. So here's, again, this molecule has symmetry, so it doesn't matter if we pick the left or the right. This is the alpha carbon. Okay. That's going to form a 6-membered ring when the alpha carbon attacks the carbonyl carbon on the right. Remember, we kick off ethoxide, so just connect the dots. Don't draw OET in your molecule. So we're going to have a 6-membered ring. Okay, so here's my alpha carbon, carbon 1. Carbon 3 has 2 methyl groups. Carbon 6 has a ketone. Carbon 1 has a bond or a line to an ethyl ester. Okay, so check that it has a keto group or a ketone at the beta carbon with respect to the ester. Okay, so that's it for this section. I hope you understand a little bit about the Claisen and the cross Claisen and how to control it with esters that have no alpha hydrogens, or directing it very carefully using LDA. The intramolecular Claisen reaction is named after Dieckmann, and that's a very powerful reaction for forming carbon-carbon bonds and rings. Okay, thanks for watching, and good luck studying.